Network. Today we are starting our new season with Dr. Yude Pan. And for those who haven't joined us before, we are the International Tree Mortality Network, which is an initiative of the UFRO Task Force and a group that tries to understand trends in mortality over time at a global scale and connect between different types of data to actually get this global picture of the trends in tree mortality. We have been promoting these webinars, and so they happen every 6 to 8 weeks. So please follow us on Twitter. We'll put the details of the Twitter account in our in the chat. And just before we start, I have a few housekeeping rules. So first, this presentation will take around 30 minutes, and then we'll have 30 minutes questions. If you have any questions, even during the presentation, feel free to ask them, but not using the chat. Please use the Q&A function and ask your questions there at any time. Normally we get too many questions, so sometimes we don't have the time to answer all of them. So we'll try to address the more questions we can, but don't feel upset if your question is not asked. And please use the chat only to report any technical difficulties, but now you can introduce yourselves using the chat as well and talk to others. I'm very pleased to introduce today Dr. Yude Pan from the USDA Forest Service Northern Research Station. Yude has a bachelor's in applied mathematics from the Oceanography University of China, a master's in quantitative plant ecology from the Graduate School of Chinese Academy of Science, and a PhD in plant ecology as SUNY ESF and Syracuse University. Yude has contributed massively to our understanding of the patterns in the global carbon sink. And today she's going to present her talk on the impacts of disturbances on leaf area index and productivity of the terrestrial ecosystems. So thank you very much, Yude, for joining us today. I'm very happy to have you here. And now I pass it on to you.
So I can start it, right?
Yeah, you can start. Thanks.
So in the recent year, there are quite a few remote sensing-based studies suggest that global have become greener or been greening. So this map made by Boston University shows that the leaf area increased on most lands over the last 3 decades. So this is the most recent global carbon budget. So we can see that the fossil fuel emissions and the emission from land use change and carbon absorbed by ocean remained in the atmosphere. So the imbalanced carbon is supposed to be taken by terrestrial ecosystem. So that is terrestrial carbon sink, which is 3.4 gigaton carbon. So this study group reported the global carbon budget every year, which shows that terrestrial carbon sink has been continuously enlarged over the last 2 decades. So what's the cause for this greening and the enlarged terrestrial carbon sink? The global DGVM models suggest that the major driver is likely the elevated atmospheric CO2 concentration. We all know that leaf area is closely related to primary production of vegetation. However, in the reality, we did not have the quantitative relationship available for the estimation. In our recent studies based on CO2 enrichment experiments, we found there's a close relationship between the enhanced leaf area index and the enhanced above ground primary production, ANPP. So this relationship fits for the different vegetation type. So it has an implication because the equation is empirical and derived from CO2 experiments. It means by using it, if we know the changes in LAR, we can estimate changes in vegetation productions affected by high CO2. So with available global LAR data set, we can make a global application of the equation, which is a logistic equation. So this map shows LAR changes between the 2000 and the 2015. This is a ratio change. Green color means LAR had an enhancement, and red, warm colors means a reduction. So over the time, 69% of vegetation land had enhanced LAR, 1% no change, and 30% with decreased LAR. So this map is not as green as the map made by Boston University, but I think it's not quite exaggerated that lands become greener. This is also LAR change, but these are real values of LAR, not ratio. So shows LAR gains or loss. You can see they are very uneven under the land. Some places appear to lost quite a lot LAR, and some places gain a lot. So the losses in LAR will mainly caused by disturbances. From these LAR changes, we can recognize 3 types of disturbances. First, human disturbance. For instance, we can see that deforestation and agricultural expansion in the areas around Amazon forest, Congo River, and in the eastern coast of Madagascar, and some oil palm plantation in the Southeastern Asia, all resulted great loss in LAR. Other disturbances are nature type related to changing climate. One is increased wildfires in the boreal and the tundra zones. The trademarks of wildfires are those fire scars. The wildfires can white up vegetation canopy, reduce LAR to 0. So such disturbance appear to be more intensified in the Eurasia continent than North America. So the affected area appear to have those fire scars interweaved with the areas with LAR increase. So to form those kind of mosaic mingled together. Another climate-related disturbance recognizable are drought effect. So the droughts include decrease in precipitation and also the heat-induced drought. So we can see in some very dry areas, such as the semi-desert of Kazakhstan, and the Brazil Cantina, Andes Coast Desert, Southwest US, and Australian outback. So all those red and pink colors shows losses in LAR. However, if we take a look at precipitation changes over a half century, we can see generally Africa and most of Eurasia became drier, but not at all in the New World. So not all those dry places with the loss of LAR receive less precipitation, such as Southwest US and West Australia. So the loss of LAR was more likely related to heat-induced drought. So it means that in the very dry land, impact of high temperature could outstrip any benefits of improved water conditions, either by increased precipitation or by elevated CO2. So, however, many dry land had high increase in LAR, such as Mediterranean regions, India subcontinent, and Australia open woodland. Especially the high LAR gains appeared in the temperate zones across continent. So the zones include not only temperate forest, but also major farmlands and grassland, such as the Great Plains in the US. In response to changes in LAR, ANPP had enhanced in most areas over 2000 and 2015. So green, this is also ratios. Green has enhanced ANPP, red has reduced NPP. Especially 86% of vegetation had enhanced ANPP and 14% with decreased NPP. So even some area with a slight decrease in LAR, there could be still some increase in ANPP because of direct effect of high CO2 on the photosynthesis at the leaf levels. So those is ANPP gains and loss. These are real ANPP values. It shows some high gains of the ANPP in some boreal zones in the temperate forest of Eastern US, European countries, and Northern India, and the Southeastern China. High NPP also gained in the tropical regions in both areas of forest and savannas. This is a summary table about relative changes in LAR and ANPP. Globally, LAR increased about 10%, and the ANPP about 18% over the time. So that means that the LAR increased by 0.6%, ANPP by 1.1% annually. So among this woody ecosystem, the shrubland and savannas had highest enhancement. Among the forest, the deciduous needle-leaf forest had highest enhancement. The deciduous broadleaf forest and mixed forest, mainly the temperate forest, had modest enhancement, while the evergreen broadleaf forest, mainly the tropical forest, had the smallest enhancement. We also see very high enhancement in the croplands, urban area, and the grassland. So this is a summary table about ANPP and the change. These are real values. So global ANPP was changed from 54 gigaton carbon in 2000 to the 63 gigaton carbon in 2015. So with enhancing, gained about 8.8 gigaton carbon annually. So this is really remarkable gains. Among all the ecosystems, the evergreen broadleaf forest had highest above ground production, following by savannas and the grassland, because these two ecosystems have vast land. Although evergreen broadleaf forest had the smallest ANPP enhancement, they still gain quite a large production, about 1 gigaton, because of their high productivity. The small enhancement is because these forests are more saturated with LAR and have less room for leaf expansion. So forests together gain about 2 gigaton carbon production, while the savanna, grassland, and the cropland also gained the large amount of ANPP. So at first I thought it looks like forests did not have much advantage than other ecosystems. Then I realized that this study is based on the MODIS land cover classes, which define forests as with the tree cover greater than 45%. However, FAO definition of forest is the land with the tree cover greater than 10%. It's very different. If we use FAO definition, most of the woody savanna, a part of savanna, would be classified to the open forest. So if we could add this production into the forest, this is going to make global forests, doubtlessly the dominant of terrestrial production and carbon sink as we expected. We also compare our results with the MODIS model result. So this is the changes in ANPP between during the time estimated by MODIS model. So we can see very different picture. The MODIS model estimated huge NPP loss in most of South America, Southern Africa, and tropical Asia. It also estimated great NPP decrease in the boreal forest across Eurasia, in the southern US and southern China. It does estimate the increase of ANPP, such as in the central Brazil and African forest, and the boreal forest in the North America. Comparing to 14% area with the ANPP decrease estimated by empirical model, the MODIS model estimates by the 41% of vegetated land with decreased ANPP. So here's a difference of ANPP estimated by an empirical model and the MODIS model for 2015. So the empirical model estimated much high ANPP in the Amazon forest and in the Southeastern Asia, but less in the Central Africa, the Brazil and Bolivia. The empirical model also estimated high NPP in the boreal forest, but less in the tundra zones. So the mechanism behind the difference reflect the modeling with or without fully incorporating impact of high CO2. The major driving force in the MODIS model was climate and drought effect. It did not have the CO2 formula in the photosynthetic equation, so did not fully account the high CO2 effect for alleviating drought and enhancing photosynthesis directly. Now let's back to the early question about enlarge the terrestrial carbon sink. Because above ground NPP is only part of ANPP, total NPP. That's about 67% on average. After big carbon release from hydrotrophic respiration, the left NEP is about 30 to 40% of NPP. And the final term for carbon sink is NBP, net found productions, which is about 40% of NEP. So after all these conversions, the enhanced NPP, that's 8.8 gigaton carbon, equals about 1.8 gigaton carbon enhancement in terrestrial carbon sink. So this number matched amazingly well with the estimate by Global Carbon Budget, which estimates a terrestrial carbon sink in the early 2000s to be a 2.4 gigaton carbon and to be a 4.1 gigaton carbon in the 2015. Here are some sort of conclusions. 3 large-scale disturbances on land that can be recognized from global LAR changes, including human disturbances in tropicals and climate-related natural disturbances of wildfire and drought. over 2000 and 2015, 68 of vegetated land had increased LAR, while 86% had increased ANPP. The major drive for LAR and ANPP enhancement is likely the elevated atmospheric CO2 concentration. As many studies report increased tree mortality in the different forests, we observe the severe consequence of nature disturbances on LAR and ANPP, but also remarkable enhancement in LAR and ANPP globally. So this result may suggest that global terrestrial carbon dynamics and cyclings have been accelerated by both positive and negative environmental impact over the last few decades. Okay, that's it.
Thank you, Yude. Thank you very much. I can see a few questions coming up in the chat already. And I will pass over to Tom Pugh, who is going to host the question and answer session.
Cool, thanks, Adriani. Thanks, Yude, for a really interesting talk. So I'm going to start with a question here from Daniel Amago. They ask, could you elaborate more on discrepancies between your results of ANPP and that of the MODIS model?
He wants to see more about that?
Or understand the discrepancies between what you presented and the MODIS model.
Oh, yeah, that's what I said. Because our model is empirical model, that came from the CO2 enrichment experiment. So suppose this empirical model kind of cover all the high CO2 impact. So but the MODIS model does reflect some leaf area changes in their model, but the CO2 impact actually includes three factors. The first, that direct the enhancement in the photosynthesis through that stomach cavity, higher CO2 concentration. Second is that because of reduce the water conductions and get some water saving, this is also help to enhance the above ground MPP. And the third fact is that because now we have more carbon and water, so the trees or other vegetation can have those resources to get the increase in that LAR. So these kind of three factors comes from high CO2. I think the MODIS model, because they didn't formula that CO2 kind of function in that photosynthesis equations, so that's why they cannot kind of cover that effect from high CO2 directly on the photosynthesis and on the reducing water use efficiency. So that's why, why empirical model predict a much high MPP increase, why the MODIS model less. Actually, for this whole period, MODIS model totally only enhanced about 0.4 gigaton carbon increase, but the empirical model increased 8.8. You can see how much difference. I do have another picture, the figure I didn't show, because this paper still is the kind of manuscript. That's my secret weapon. I don't want to show. That's really show how this, CO2 and this enhanced the ANPP linked together. So that's why I have great confidence to say this enhanced ANPP really mainly caused by elevated CO2. Did I respond? Well, I don't know.
I think that at least for me, that helped clear up a lot. And I'm looking forward to seeing your secret weapon. But one question, so your reply just raised for me, would you be able to clarify the data that the empirical model is based on? Is it forest face experiments or much broader range of CO2 experiments?
Yes, I didn't really include a lot of the figures from that study. I think last time when I had the tree talk, I put a few of that. Yes, we derive all this data from 14 the CO2 enrichment experiments. So 6 from the woody ecosystem and 8 from the grassland ecosystem. So we really find some very interesting common response patterns. So yeah, that's actually that's another issue I didn't really talk because it's too complicated in the talk. You know, because of the CO2 experiment, they use much high CO2 concentration than the atmospheric elevated CO2. So when I use this model to project the future, I have to consider to make some adjustment of that CO2 concentration to be more realistic to the elevated CO2, in the world, in the nature world. So the method I use the FAQA model. You know, the FAQA model really kind of simulate how these different CO2 level affect that photosynthesis rate. So basically, our future projection is much more kind of the I didn't show that, but after I used that the FAQA model to adjust that, actually the enhancement during this period is not 8.8, it's rather than 7.4, something like that. They become much less than that. So yeah.
Cool, thank you. There's a couple more questions kind of following on from this theme relating to limitations or potential limitations on photosynthesis. So we have one from Daniel Nadal Sala. He asked, did your empirical model include any nutrient limitation on photosynthesis? And also, did MODIS include such effects?
No, I think this is very different from the like MODIS, like more factorial type of the model. They kind of similar, kind of include. I don't think that the MODIS model have some nutrient the formula there too. They pretty much like have some leaf area and the light and the temperature and precipitation. But they still like a factorial, type of the process, the model. The empirical model is it's just a simple equation to show that relationship. So, but we think because those LAR is very sensitive to changes in the temperature and precipitation and all kind of other environment factors. So it is kind of the brings all the relationship within this equation. Another trick I didn't really tell you, because you can think LAR and ANPP, they changes every year. So if you want to compare in the beginning year and ending year, you cannot do it because they really kind of the 1 year thing. So what I did, that's why, you see those MODIS model, they never really compare current with the past. So what I did is I used the first 5 years of the LAR or NPP and the ending 5 years of LAR and NPP. So the kind of sort of an average, and then to see that difference. So in generally, we can see that the trend during this period of time. Otherwise, we cannot really do a kind of good comparison. This is what I did. So no, this empirical model does not have any kind of individual effect. And also, actually the CO2 experiment, some of the experiment, they including that nitrogen, addition, or some even include some water, multiple factors experiment. So no, when I use this data, I want to just focus on the CO2, the single factor. So I didn't use the result from that with multiple factors. I only use that from the single, CO2, enhancement. So but we did see from some results that shows that in some point that the enhancement got kind of restricted. We kind of think really kind of related to some sort of nitrogen limitation.
Okay.
But the model didn't really reflect that.
So, and you mentioned, there's another couple of questions following on the same line, and you mentioned earlier that your model took into account the water use efficiency effect. So these two questions relate to available soil moisture. So one from Sue Quick is, do you think that changes in available soil moisture, for instance from drought, has affected particular areas of the globe for the change in LAI and NPP? Or
yes.
mortality?
Yeah. Yes, I do. So you can see that, I don't know if I kind of really totally got that question, but I think from the result, we can see some dry land really got a very high enhancement in LAI and ANPP, but not very, very, very dry place. Because very dry, as I said, the temperature might be, have more impact, because they do supposedly still have some sort of effect, but cannot, the override that the high temperature effect. So in that way, in some very dry places, you just still see the loss in LAR, but in some moderately less dry, like Mediterranean region and some kind of moderate dry area, you can see very high enhancement in ANPP LAR. So that's why I think the CO2 does kind of have impact. Did I answer the question? Is that a question on the modeling or among the result for the results?
I think it's about the result itself.
Yeah, I do think yeah. Obviously, in some dry, and also there's quite a complicated. I better maybe not to confuse people. So we see actually in the temperate zones, we got very good, enhancement. So I think that's because there's either this temperate the vegetation, they have space to get expansion of the LAI. Also, they have a good kind of the growth condition. We also see some man-made system like a cropland, huge enhancement, and urban area. I think those man-made ecosystem, perhaps they also provide some water, irrigation, and also nutrient. So these things help that with high CO2, with all these other conditions to provide. They got actually the cropland, if you look at the ratio change, they got highest than any vegetation, the cropland. I kind of a little bit, unsure about this result. Then I check, there are quite some, not so many studies as other nature system. The croplands, a lot of cropland, they did show kind of very high enhancement, but those man-made systems certainly quite different from the nature systems.
Cool. Okay, so moving on slightly in the theme of the questions, we have one from Arturo Sachez, and he asks, so when you're comparing, or MODIS LAI, when compared with ground LAI data, performs very poorly, what is the uncertainty in your modeling when data from the empirical model is compared with available LAI field data? So how well does your model compare to field data compared to how well the MODIS model?
Oh, okay, yeah. I think this is a problem for perhaps all. No, I haven't really kind of I don't know if you say the LAR data, because we use the LAR, there are quite a few LAR data sets today. So I think the data I use from Dr. Jimin Chen's group, I think I showed like the global veg 2 or something. At least they claim, they have the paper, I think in 2019, published in the Nature Communication. At least they compare several LAR data sets. and try to show their data set is much better than the other data sets, you know. So no, I didn't really, but suppose we predict the ANPP, we better to do some sort of the validation, right? No, I haven't really done that. I think the not only my model, many other models, like at the beginning, I kind of mentioned the DGVM model. They think that those increase the carbon sink or something they related to high CO2. They use model to predict that. They also have the problem about no real data from measurement to validate their model results. Yeah, I think, but I think this is a really good question. I need to think of that. I think there are some sort of data, not very many, perhaps, but perhaps we can still find some to do validation. So I think in that way, at least we can give more, confidence to this study. Actually, there are a lot of uncertainties in this empirical model. I kind of already finished the draft. I mentioned quite a lot of a few issues. I don't know if I can all list here, but they do have a lot of uncertainty. Even like what I said, the land classes. You know, I mentioned that because those modest land classes. You know, if you use that, that's globally only have about 20% of forest, compared with the of all the vegetation, and compared to the FAO, they had at least about 1/3 of the land is kind of covered by forest. You can see how much different. But I guess that's because those land cover maps all developed based on remote sensing data. They have some sort of limitation for kind of classify some, particularly in those zones, with the, not like totally for in those transition zones or something like that, quite fuzzy, it's kind of hard to do a good the classes. That's why they use forest have to be 45% of tree cover rather than 10% of tree cover. So yeah, but they do have a lot of uncertainties. I'm pretty sure about this studies. Yeah.
Great, thanks, Yude. Then I think we just have time for one more question, and on that we'll take a bit of a different angle. So Manish Kumar asks, so in the context of the COP26, talking about planting trees or managing the landscape as two potential options, I think, for carbon sequestration, which do you think is a more powerful approach for mitigating the climate crisis, they ask?
I think, I would think more for stop deforestation. So because the most of deforestation we can see happened in the tropical regions. When you see that global ANPP, above ground ANPP, we can see that totally about 64, 67 gigaton ANPP, the production. But that's the concept about the terrestrial carbon sink. Terrestrial carbon sinks only means those vegetation take extra carbon because of those high, atmospheric CO2. But suppose that the ecosystem have some sort of balance, that they can take a lot more, the production, the carbon every year, but they have some sort of balance, between the land and the atmosphere. But if you cut those trees, okay, there are two effects. One is that the lot of carbon lost from those the large carbon stock from trees. And second, you reduce the capacity of the forest. They stay there to kind of make photosynthesis to uptake carbon. So about plantation, of course, is important, but I think now most of the places is just some edge place, some place perhaps you can grow in a lot of trees, but perhaps not really as significant as the trees in the tropicals. That's my point. Perhaps you can, but it still can help. But I think stop the deforestation in the tropicals more kind of the critical. I don't know if I answered the question right.
I think you answered the question, yes. Well, at least from my perspective, I can't speak for the questioner. But thank you very much. I think that with that, we will close the question session. And thank you, Yude, for a very interesting talk and stimulating discussion following on from that. So much appreciation. And it's difficult to do round of applause, but I'll do a Zoom round of applause.
All right. Thank you very much.
I will pass over to my colleague Rupert just to round up.
Okay, thank you. Thank you very much. Yeah. Bye-bye.
Yes. Thanks again also from my side, both to Yude for the great input and also to those asking questions and to those listening in. I have the pleasure of announcing the next seminar before closing this one. So mark your calendars. The next seminar will be on December 9th at 2:00 p.m. Central European Time and 4:00 p.m. Moscow Standard Time. And our speaker will be Dr. Vyacheslav Karuk from the Russian Academy of Sciences. And Vyacheslav will be talking about the conifer decline and mortality in Siberia. So we'll be moving our focus to the large boreal forests of Siberia and talking about mortality there. This will be another exciting seminar, so mark your calendars, and it would be great to see many of you there also within 2 weeks' time. Thanks again for joining. Thanks again for being here. And with that, I'm closing the session and hoping to see you all in 2 weeks. Goodbye.
Bye-bye.
Bye.